Greetings, welcome to lecture number 12 on basic circuit theory. I am Razavi. Today we will continue our understanding of Norton and Thevenin equivalent circuits and extend the idea to what we call source transformation. It's a pretty simple concept, but it is used sometimes, so it's good to go over it. And then we will go on to two more electric quantities, namely energy and power, and see how they are quantified and try to derive the results for a resistor, for example. And then we will be able to use these results to predict when power can be transferred maximally from one circuit to another circuit. And we'll have to see why this is a big deal and why we care about it. Okay, but first let's start out with a quick review of the last lecture. So we saw that we looked at Norton's theorem, which is similar to Thevenin's theorem, and we said that if we have a circuit and we manage to decompose it into two sections, A and B, that are connected by only two wires, then for A or for B, we can simplify the circuit to a current source in parallel with the resistors. So for example, if I am interested in A, I can replace it with a current source, Norton current, and a resistor, a Norton resistance. And then section B is still attached, and we can solve this circuit more easily than this one. Okay, and Norton said in order to find the equivalent circuit of section A, first of all, we take section B away, so we just have that. And then we short circuit these two wires like so, and find the current that is generated in this wire by the circuit. The circuit has some input, so presumably they want to generate currents and voltages, and there should be a current there. Now, we measure that current becomes this current source here, the value of that current source. And then we also need this resistance. To find that resistance, Norton prescribed the same method as Thevenin did. Namely, we just have to kill all the independent sources in the circuit, set them to 0, and then we have to find the resistance that we see between these two wires. And we can just do it by inspection, or we can officially apply a voltage source from outside and measure the resulting current, and Vx over Ix will be the resistance that we are looking for, and that's what goes here. So that's how we construct a Norton equivalent. All right, so because we have a Thevenin equivalent and a Norton equivalent, in some circuits we might decide to go from one to the other. So, and that's what we call source transformation. So let's talk about that and see what that really means. So source transformation. So I'll show you an example. Suppose I have a current source like this, I1, and then I have a resistor like this, R1, then I have a resistor here like R2, and then I have a resistor here, R3. And I am interested in this voltage as the quantity of interest, V out. Okay? So of course the circuit is not that hard to analyze. You can use node analysis, mesh analysis, Thevenin's theorem, Norton's theorem, whatever you want. But also, if we just look at the circuit, we see that this resistor and this resistor are in series, forming a voltage divider. So we're thinking, if we also reduce this to something else that had a series resistance, that series resistance and this would all be in series, so the circuit would be simpler to analyze. So that tells us that perhaps we should replace this combination with a Thevenin equivalent. This looks like a Norton equivalent, right? So we replace it by a Thevenin equivalent, and that's what we call source transformation, meaning that this current source and this resistance are converted from this Norton equivalent to a Thevenin equivalent. So here's our job. We want to go from this circuit to this circuit. So we have a voltage source, call it V1. Then we have a, call it VT, Thevenin resistance, and a resistance RT. So I'm hoping that I can do that. And if I do that, then the result might be quite easy to analyze. So I'm trying to replace this box with this box here. Okay? And the rest of the circuit, of course, remains the same. So we have R2, then R3, and then V out. Okay, so how do I go from the top of green box to the bottom green box? Well, it should be easy, right? The Thevenin voltage is obtained by looking at these two wires, the voltage between these two when nothing is connected. That's what Thevenin told us, right? Thevenin said, look at the voltage between these two wires when nothing is connected, and this circuit is generating voltage. We're trying to measure that. So let's focus on that and see how much voltage this little circuit generates here, right? So we probably have to draw that separately so that it's easy to visualize. So here's I1, here's R1, and here's the voltage that we're trying to find. This voltage is the Thevenin voltage, right? According to this method. How much is that voltage? Well, you see that I1 comes in, flows from high potential to low potential, so I can just write Ohm's law. So I can say VT is just I1 times R1. Okay, so that's easy. We write here, this is I1 times R1. This is the actual value of this voltage source, right? VT is just a name that we invented just now, right? But the actual value would be I1, R1. How much is RT? Thevenin says, kill all the sources in here, sit here and see what resistance you find. So we kill this source, we set this source to 0. If this source is set to 0, it's an open circuit, so all that is left is this R1. So R1 now becomes RT. So what you can see is that we went from the top green box, which looks like a Norton equivalent, to the bottom green box, which looks like a Thevenin equivalent. And this is called source transformation. So anytime you have a current source and a resistor in parallel somewhere, maybe it's good to stay with it, or maybe if you convert to a Thevenin equivalent, the result will be simpler to analyze. And of course, vice versa. So, can I find V out here? Yes, it's pretty easy, right? Because now I have a voltage divider. So I can say V out is equal to this resistance, R3, divided by the sum of these three resistances. So that would be RT, which is R1, plus R2, plus R3, multiplied by this voltage, right? It's a voltage divider. How much is this voltage? I1, R1, I1, R1. So we found the output voltage with minimal effort in this case. So by source transformation, we mean either going from a parallel combination of a current source and a resistor to a series combination of voltage source and a resistor, or the other way around, going from here to here, depending on what we're trying to do in a given circuit. All right, so that's all there is to it in terms of source transformation. Okay, let's talk about energy and power. So we're going to talk about energy first. All right, so you might remember how energy came into play at the beginning of this course when we were talking about the concept of voltage. So the way we defined voltage was that if I have two nodes in a given circuit, and I have a certain voltage difference between these two nodes, for example, from here to here, I call this V. So if I put a voltmeter between these 2 points, I measure V volts, right? 10 volts, 5 volts. Okay, so what this means is this voltage is actually the amount of energy necessary to take positive charge from here to here, and we have to be careful about that. So suppose I want to take a certain amount of charge, Q, from here to here, right? So the energy necessary to do this is given by the charge that I have to take times the voltage, right? When we talked about the voltage at the beginning of this course, we went the other way. We said voltage is defined as the amount of energy necessary to take this charge divided by the charge, right? But now I can just write it like that. So the energy that I have to give to this charge to take it from here to here across V volts of difference is given by the charge itself times the voltage difference. All right, so that's the amount of energy that we have. Okay, but this is a little suspicious. Why? Well, so let's put a question mark here. It's suspicious because am I sure that while I am taking Q coulombs of charge from here to here, this voltage does not change? Why should the voltage change? Well, for example, if you have a capacitor, you might remember this, right? And you take some charge from this plate to that plate, then the voltage of the capacitor changes because the voltage and the charge are related. So as I move this charge, let's say electron by electron or proton by proton, right? Positive charge. As I move this charge from here to here, bit by bit, I'm not sure that this voltage is constant during the time I'm making this charge transfer. If the voltage is not constant, then I cannot write this, right? V is a function of Q and so on, so we can't do that. All right, so we have to find a better definition that doesn't have this ambiguity in it. And the better definition would be the following. What we do is the amount of charge that we move from here to here is very, very small, so that when we move it, the change in this voltage is negligible. So in other words, we're looking for a change of an amount of charge that is very small, infinitesimally small, and that charge, when I transfer it across V volts, requires a very small amount of energy. And the hope is that this charge is so small that while I move the charge from here to here, this voltage changes negligibly. All right? So this is the actual definition of energy in this context in terms of the voltage difference between two nodes. We just move a small amount of charge and we find the small amount of energy necessary to move that charge. That is the energy that we need. All right, so that's the official definition of energy that we use in our circuits, in our domain. All right, that's great. Now, in most cases, actually, we are interested in power. So energy is the amount of work that we did to, for example, to move this charge. There's a one-time deal. But power has to do with short-term energy transfer. So let's talk about that and see what that means. So power. So the official definition of power is the rate at which energy is used. Energy is given or energy is taken. So definition of power is dE over dt. So let me give you an example. If you buy a light bulb and the light bulb is rated at 20 watts, what does it mean? So we have a 20 watt light bulb. Okay, so watt is the unit of power. So it means that the power dissipated by this light bulb is 20 watts, right? This P. So that means that P is 20 watts. Now what does that mean? What that means is the following. If we 20 watts is actually the amount of energy, so 20 joules per unit time in 1 second. So what this means is that if the light bulb is on for 1 second, it will draw 20 joules of energy from our power source. All right, so that's what it means. Of course, the assumption here is that everything is constant, so this derivative reduces to just energy divided by time, but you get the message. So power tells us how fast we are consuming energy, right? If you have a 100 watt power, then that 100 power in 1 second draws 100 joules instead of 20 joules. So it draws more energy per unit time. It dissipates energy faster. And that's the notion of power. All right. From the other perspective, you can also say if I want to find energy in terms of power, then energy is just the integral of power with respect to time, right? So from some time to some other time. So for example, if you have a light bulb, a 20-watt light bulb that is on for, let's say, 1 hour, then the total power consumption, the total energy will be 20 watts times 1 hour. And sometimes that's called 20 watt hours. 2 watt hours is actually similar to joules. It's a unit of energy. If you look at your electric bill, the electric bill specifies the energy that you consumed in 1 month in watt hours or kilowatt hours. So that's actually in joules. All right? Okay, so we can go either way. But of interest to us is calculation of power in electric circuits. So we want to see if we can simplify that result so that we can readily write an equation if we want to find power. All right, so that shouldn't be that hard. So let's change the color of the pen here and see what we can do. Okay, so power in circuits. So I have some circuit and someone says, how much is the power dissipated in this resistor? So we would like to find it, right? Why does it matter? Well, it could be that that resistor has to have a certain power rating, otherwise it burns out. Or it could be that we're trying to see how much power we are burning, dissipating, how much heat we are producing, and those are things that we don't like, so we're trying to minimize that. So there are many different reasons for looking at the power of dissipated by some component. All right, so what I can say is that I have this equation. So let's start out with this equation. dE is equal to V dQ. And now what I will do, I will say, okay, so let's write this as, so we know that power is dE over dt. All right, the rate at which energy is consumed. Now I'll use the chain rule in this equation. So I'm going to write it as dE over dQ times dQ over dt. That's okay, right? All right, so what is dE over dQ? dE over dQ is the voltage difference that we have, whatever the device is, right? So for example, you have some sort of device here, and that device has a voltage difference of V across it. That V could be time varying or not, doesn't matter, right? So it's a certain V. So this part is the voltage across the device. And then dQ over dt, what does that mean? It means the rate at which charge is moving through this device, right? And that's what we call current. So dQ over dt is I. That's the rate at which charge is moving. Remember the definition of the current at the beginning of this course? All right, so then that means that P in general is equal to V of t times I of t. Both of these are functions of time in general, right? It could be that they're constant or not. So this equation is always valid, regardless of what we are looking for. And to emphasize that it's a function of time, sometimes we call this the instantaneous power. So we call this instantaneous power. All right, so if you say at any moment in time, for example, across this device, there's a certain current, there's a certain voltage, we multiply those at that point in time, that gives us the power that is drawn or given to this device at that moment. All right, so that's great, and from this we can readily use the equation to find the power, for example, consumed in resistors, right? So let's look at an example. So we have a resistor here given by R1, there's a current I of t, and there's a voltage V of t. and we want to find the power consumed by this resistor. You know that when current passes through a resistor, the resistor takes that power given to it and converts it to heat. So the resistor gradually warms up. Of course, whether we can feel the warmth or not depends on how much it heats up. But in general, a resistor just dissipates the energy in the form of heat. Right? The energy cannot go back to the circuit anymore. All right, so we need to apply this equation to this device to find the power equation for a resistor. That's the quiz of the day. I'll give you 60 seconds to think about it and see what it will look like. So, what did he get? Well, we know that V and I are related by Ohm's law. So I can just say that P is equal to V of T times I, and I is V over R1. So V of T over R1. So that's the equation that we remember, V squared over R1. That's one equation. Or I can replace for V, so I can say it's I of T from here, and then V is what? V is IR, so I squared times R. So those are both valid equations. You can use whichever you want, V squared over R or I squared times R, right? Whichever you want. So those are very simple equations that we have for the power consumed by a resistor if it has a voltage of V across it, or if it has a current of I through it. Let's talk about something that we see every day, the lamp post. We know that we have lots of lamp posts that turn on at dusk when the sky is getting dark, and then they turn off at dawn when the sky is turning light. How much power do these lampposts consume in a typical city? Well, we can do a quick calculation to get a feel for the numbers. Imagine that we have LED lights, so they are somewhat power-saving devices. And suppose that a medium-sized city has 50,000 of these lampposts. And each of these LED lights consumes 100 watts. These have to be pretty strong LED lights so that they can provide some lighting on the street. So that adds up to 5 megawatts of power. That's equivalent to the power necessary for some blocks of town. It's a lot of power. In fact, typically what happens is that in any given city, somewhere between 20 and 50% of the city's energy cost just comes from the lampposts. So that's enormous, both in terms of environmental issues and in terms of just cost. So can we make these lampposts smart so that they consume less energy? How can we do that? Well, yes, there has been actually some work in that direction. And this picture is a little hard to see, but imagine it's nighttime, and these are streets, and they have lampposts periodically spaced along the road. Now, ordinarily, these lampposts don't have to be turned on at night unless some vehicle is passing. So what we do is we have some sensors inside the lamppost that detect the presence of a car. And as a car arrives here, these lampposts turn on. And as the car moves along, as it gets close to a lamppost, the lamppost turns on, and the other lampposts turn off. So this is just a lamppost acting on demand. If there is a demand for it, it turns on. If there's no demand for it, it turns off. So for many of the streets in the town that don't have much traffic at night, this is a great savings in terms of power consumption. Now, if we are going to make the lampposts smart, maybe we can add some other features as well. So here are some other thoughts that have been directed to the notion of smart lampposts. You can imagine that many other things can be added. Now the font size is small, but I'll read them to you. We see that, for example, you can have wireless transceivers attached to this, so Wi-Fi, Bluetooth, that sort of thing. We can have, for example, digital signs here, like a display, that show various information, for example, traffic direction or advertising and so forth. These are just simple digital displays. We can have image sensors that detect, for example, if there's a pedestrian in that vicinity, and even for security purposes. We can have speakers that broadcast music or announcements, and many other devices. So lampposts, these simple old lampposts, actually hold a great potential for many interesting devices that we can attach to them. Isn't that beautiful? All right, so based on that, now we can go ahead and extend the idea to the notion of maximum power transfer. So let's see what that means. All right, so we decided that if I have a resistor anywhere in the circuit, and I know its voltage or current, I can readily write the power that is consumed by the resistor instantaneously as a function of time, right? It would be like this. Of course, if the voltage is constant, okay, so just don't worry about the t here. All right, so let's talk about the notion of power transfer and why in some cases we care about maximum power transfer. So power transfer. Well, we have seen that if I'm given any circuit that has only two wires coming out of it, I can model it by a Thevenin equivalent, right? Something like this. So any circuit that reduces to this situation can benefit from this model, and then the results will become very interesting. So let me give you an example. Suppose we have an antenna. This is the symbol for an antenna. Okay, so for example, the Wi-Fi system in your mobile device has an antenna that receives signals from somewhere, right? This antenna picks up the signal that's coming through the air. The antenna converts this signal, the electromagnetic signal, to an electric signal, to a voltage. So if I sit here, I can measure voltage as a function of time, right? Some voltage as a function of time. All right, okay, so we see this whole thing, if you put it in a box, is generating a voltage, right? So let's put this in a box. And of course, this is really with respect to ground. So there are two wires coming out. This is ground. And we see that this box generates a voltage. All right, so then it generates a voltage. It has two wires coming out. So maybe we can model it by Thevenin equivalent, right? So, okay, I need a voltage source, obviously, because I have to have a voltage generated somewhere, right? So that's my voltage source. And then the question is an antenna an ideal voltage source, meaning there is no resistance here? And the answer is no, there is actually a certain amount of resistance, typically around 50 ohms. So that's a resistance that we have here, and typically is around 50 ohms. So this whole thing models this antenna. The antenna generates a voltage, so it has to have a voltage generator, and its output resistance or is 7 ohm resistance is not 0, it's 50 ohms. All right, so we'll take that. Okay, so here's the situation. I have received a certain amount of signal from the antenna, and that signal is now available in the circuit. And this circuit now has to drive something, right? The signal received from the antenna has to go through probably an amplifier or something, right? So the question is, if I let's put that something in here, and let's assume there's a resistor in here. We call this the load resistance. So our job is to figure out under what conditions we transfer maximum power from the antenna to this load. All right? Okay, so that's what we're trying to find out. And that's what we call maximum power transfer. Now we say under what conditions, what does it mean? What do we have that is actually variable, that's under our control? All right, well, this voltage is coming from outside, so it's a certain amount of voltage. This resistance is given. This is the antenna that has been designed. That's not negotiable. We cannot change it. But this resistance is under our control. This is a part of the circuit. I can make it smaller, make it larger. So the question is, under what conditions, for what choice of RL, do I have maximum power transferred from here to here? All right, so that's what we're looking for. Okay, not a problem. Let's go ahead and calculate that. All right, so we're going to say P sub RL. So the power delivered to RL is equal to, let's go with this equation. The voltage across the resistor squared divided by the resistor, right? So I'm looking for some voltage here, V. So V squared over RL. So we say V squared over RL. Whether it's a function of time or not doesn't matter. So that's the power that we have. Okay, how much is V? V can be found in terms of these guys, right? It's a voltage divider. So we have 1 over RL times this voltage. This voltage is given by this resistance divided by the sum of the two times this voltage. So it's RL over RL plus RT times the VT squared. This is the power delivered to the load in terms of the Thevenin parameters of the antenna. This is the model that we have created for the antenna. And then this load resistance itself, RL. Okay, so of interest to us is how we can vary RL so as to maximize this. It's very simple. We have a function of RL. What choice of RL maximizes P? So we have to take the derivative with respect to RL, right? So we take the derivative of power. So PRL with respect to RL, and we equate that to 0. All right? And then that gives us the condition. So you can see that one of these cancels with one of these, and VT squared doesn't matter, it's just constant. So we just have to take the derivative of this, right? And take the derivative of that equate to 0. And what comes out is very simple and very nice. So that tells us that for this to happen, for the derivative to be 0, we have to have RL equal to RT. All right? Okay, so that is a very interesting and beautiful result. It says that if I have some circuit that can be modeled by a Thevenin equivalent, right? It could be an antenna, it could be anything. It could be this microphone here, right? Anything that can be modeled by a Thevenin equivalent. And this has to drive a load, a resistance, RL. Then the power delivered to that load is maximized when the load resistance is equal to the Thevenin resistance. And sometimes we call this the source resistance to be more specific. So this is also called the source resistance. So in other words, for maximum power transfer, we want the load resistance to be equal to the source resistance, right? That's when that happens. So that's something that, for example, we can try to do. If you have an antenna here, the antenna has a 50 ohm source resistance, and we want to connect it to something else to deliver maximum power, then we have to choose this to be also 50 ohms. That's the condition that we need to observe. All right, so this is a very simple result. A few words about this. When this happens, when we pick these to be equal, we say that the load is matched to the source. So we say matched condition. So generally you might hear the term impedance matching, and what that means is that I'm trying to match this guy to this guy, right? This is an antenna or something modeled by a Thevenin equivalent. There's another circuit, and we have this resistance here. So we're trying to match these two, and that's why we pick these two to be equal for maximum power transfer. So that's called the matched condition. Say the load is matched to the source. All right, but then there's one more point that we have to keep in mind, and that is the following. This is a famous interview question, so let me go to the next page and write this because it's so important that you remember this. So, caution. All right, in the interview, this is what you're going to get. You get V1, a voltage source, R1, and RL. Okay? And the question is, under what conditions is the power transfer to RL maximum? Right? So, under what condition is the power delivered to RL maximum? And you're thinking, oh yeah, that's the matched condition that we had in mind. So sure, RL must be equal to R1, right? So your immediate reaction is to say RL equals to R1. Okay? But that's not always true. Why? This result that we derived just now assumes that the voltage source and that resistance R1 are fixed. They come from, for example, the model of an antenna. We can't change those values. So this condition holds only if RL is variable, but R1 is not. All right? So this is true only if RL is variable, meaning it's under our control, but R1 is not. But when the interviewer asks you this question, he or she is not specifying what's variable, right? So you have to be careful. You say, okay, if R1 is fixed, then yes, RL has to be equal to R1 for maximum power transfer to RL. On the other hand, if R1 is not fixed, meaning for some reason you have the ability to change R1, then under what condition do we have maximum power transfer from here to here? Right? So we say R1 is not fixed. Okay? All right, but RL is. So it's the other way around. So can you guess what condition we need in this situation? All right, well, if it's not that obvious, we can write the equation again. So we say P sub RL is equal to 1 over RL. Remember from the previous page, we had RL, we have voltage divider, so RL plus R1 times V1 squared, right? That's the equation we have for the power delivered to RL. And now what I have is RL is fixed, but R1 can be changed. So what value of R1 maximizes this result? You can see that R1 has to be 0 because it's in the denominator, right? So in this situation, R1 must be 0. So these two cases are extremely important. Whether you have this or you have this has to be specified, right? We have to see in a given application what's what. But if I just ask you in the circuit under what condition we have maximum power transfer, you don't know because it just depends on which one is fixed and which one's not fixed. This sort of makes sense because if R1 is 0, I have allowed all of this voltage to appear across RL. And that's the best case for power transfer to RL, right? Because if you have nothing here, all of this voltage across RL gives me V1 squared over RL. That's the highest voltage I can create, and hence the highest power I can deliver to RL. All right, so that is the notion of maximum power transfer. All right, so I just wanted to summarize what we have covered in this course so far before we move on to the next part of the course. So let's do a quick summary here. All right, so we started with electric quantities. And we saw that we had charge, which we don't really know what it is, current, which is dq over dt, and voltage, which is the amount of energy necessary to take a unit positive charge from one point to the other point. And then today we saw energy and power. Energy and power. Okay, we didn't really define energy because we're relying on our understanding of energy from physics, but we defined power. All right, then we talked about electric devices. And we saw a number of those. We haven't seen all of them yet. So we started out with a piece of wire. We said that the ideal wire has 0 resistance, so it acts as a short circuit. It guarantees a 0 voltage drop. And then we talked about switches. We have switches that are open or not conducting, in which case they act as an open circuit and hence guarantee 0 current. Or the switch is closed or conducting or on, in which case it acts as a short circuit, as a piece of wire. Then after switches, we talked about voltage sources. Voltage sources, both dependent and independent. And then we talked about current sources, both dependent and independent. And then we talked about resistors. Okay, these are the components we have seen so far. Of course, there are more, capacitors, inductors, etc., that we will get to soon. All right, then we talked about the basic laws governing any circuit. KVLs and KCLs. KVL and KCL, so KVL and KCL. So we saw that the sum of voltages around any loop should be 0. The sum of currents flowing into any node should be 0. And with these and the equations governing our devices, we can solve any circuit. But then we try to make this solution procedure more methodical. And for that, we looked at a node analysis. We saw that node analysis is a KCL-centric process. We're going to write some KCLs at the end. And when we solve those KCLs, we find a bunch of voltages. So we assign some voltages to the nodes after we picked our ground. We found the currents through the different branches. We wrote KCLs at those nodes. We solved n-1 equations and got n-1 voltages. Or we can perform mesh analysis, which is sort of the dual of that. So the idea here is that we identify a bunch of meshes and for every mesh we assign a current. Then we find the voltage drops across devices. We write KVLs around these meshes. We end up with N KVLs and N unknown currents, so we can find the currents. So this is KVL centric. This is KCL centric. Okay, and so again, these are just analysis techniques that help us make things more efficient. And then we looked at some circuit theorems, which again give us additional insights, give us also tools to simplify circuits. So we talked about superposition. When we have more than one input, it might be a good candidate to apply. So we keep one input, we kill all the others, we find the result. Then we kill another, we keep another input, we kill all the other inputs, we find the result, we add up all the results. This applies anytime the system is linear, because linearity and superposition go hand in hand. And then we talked about Thevenin's theorem. So Thevenin's and Norton's theorems. And we saw that these theorems allow us to take a big chunk of the circuit and simplify it to a voltage source in series with a resistor or a current source in parallel with a resistor. And again, this is a great simplification that can make the analysis more efficient. So when you're sitting here and looking at these, when you have a circuit, you don't know whether to do this, 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 right? So that comes with a lot of practice. Again, none of these is sort of the right approach, the wrong approach. It's just a matter of minimizing the mathematical labor in analyzing a big circuit. So the more circuits you solve and the more you apply these ideas, the better you will feel as to which one of these given options would be best for a circuit. Okay, and finally, we talked about source transformation today, which is a very simple case of really going from Thevenin to Norton or back. So that's also handy to have sometimes. Source transformation. And then we also talked about maximum power transfer and the concept of matching. Okay, so if I have some circuit like this, and I have some circuit like this, and I want to transfer maximum power from here to here, what I have to do is I have to pick this resistance RL to be equal to this resistance RT, the Thevenin resistance, right? Provided that this is fixed and this is under my control. If RL is something I can change, I have to pick RL to be equal to this RT for maximum power transfer from this circuit to this circuit. All right, so that's a quick summary of what we have done so far. From next lecture, we will get into RC and RL and RLC circuits, which are more interesting, more useful than what we have seen so far, but also a little more complex. So we have to build up our foundation in that direction. All right, I will see you next time.